Hello again, Chem 2 students. Mr. Keister here with you again today. This is the video for Thursday, October 8th, 2020, which is our, I believe, 35th day of school for the fall semester. Always keep in mind, though, that the dates could change for a variety of reasons, but the lessons and the order that those lessons are presented will remain the same regardless. So let's look at the do-nows and see what our schedule is for today. No new papers to pick up today. That's unusual. Your assignment for today was to complete numbers 1, 2, 3A, and 4A only on the quantum numbers and orbital diagramming assignment that you picked up yesterday. Hang on to that. We're going to continue on with that today, and you'll be able to finish it. If you want to check what you've done so far, the answer key is posted on the back board. It is also posted, of course, on the answer keys page in Canvas. For those of you that are at home. So today we'll quickly review and continue the quantum mechanical model of the atom, or quantum theory. We'll look at the Aufbau principle, which is also called the diagonal rule, orbital diagrams, and hopefully get started on electron configuration. Hopefully after yesterday's lesson and today's and tomorrow's, that things will start to all come together for you in regards to where we're headed. Your assignment is to finish the assignment that was started yesterday, and I will be collecting that tomorrow for a grade. Also, FYI, we have an exam, Unit 3-1 exam, coming up in the not too distant future. Not sure what day yet, kind of looking like Tuesday. We'll see. Hopefully I'll know that by tomorrow. It will cover the electromagnetic spectrum, speed of light, wavelength, frequency, energy, and the visible spectrum, of course, the Bohr model of the atom, and the quantum mechanical model, including diagramming of the elements by their electron structure involving quantum numbers, which we've already done, orbital notation, which we will do today, and electron configuration, which if we don't get started on that today, we will do that tomorrow. So, got a lot to do here in the coming couple of days, and let's get going. So again, we're going to flip back and forth again today between our note packet and our stapled handouts for the quantum mechanical model. We'll spend most of our time on the handouts, but we're going to get started here on the notes. So there are two other methods of diagramming the electron structure of an atom besides quantum numbers, which we did yesterday, by showing how the electrons are arranged around the nucleus in their particular energy levels and sublevels. Okay? There are three rules that govern the filling of the orbitals by electrons within the principal energy levels. And the first rule is called the Aufbau principle. It's also called the diagonal rule. Electrons enter orbitals of lowest energy first. Okay, this is just a little side note here. This is where we veer off from the Bohr model. All right, so the Bohr model of the atom, which of course introduced us to energy levels, Bohr thought that the electrons filled the energy levels by lowest energy first. So in other words, the lowest energy level in regards to energy is energy level 1. Electrons would they'll fill there first, then go on to 2, 3, 4, 5, 6, 7, and so forth. For a short while, the quantum mechanical model followed that. In fact, the electrons do start filling in level 1 and then go on to level 2. But once they get to level 3, something different starts to happen. And so this is where the quantum mechanical model veers off a bit from the Bohr model. So I want to restate this. Electrons enter orbitals of lowest energy first. Orbitals. It does not say energy level. All right, it does not say that. The diagonal rule for orbital filling is outlined by the Aufbau principle is this. It's called the diagonal rule because, as you can see, the arrows are going diagonally. Now, we have a much larger version of this in our handouts that we're going to talk about in much greater detail. But just to introduce this to you, so we fill the 1s orbital first, which of course is the only orbital in energy level 1. We would expect that since energy level 1 is the lowest energy level. When you get done with one arrow, you go to the next one. So the next arrow says we fill the 2s orbital, which makes sense. That's the first and lowest energy sublevel in energy level 2. Once we get to that, we get to the 2p, which is the second energy level, or the second sublevel, the higher energy sublevel of energy level 2. So far we're right with 4. Energy level 1 first, then 2 next. Then we go to the 3s orbital, which is the lowest energy sublevel in level 3. Again, we're right on track. Now we go to the next arrow. 3p is next, okay? Next sublevel in energy level 3. But here's where it veers off from the Bohr model. We go to the 4s orbital first. Then we go to the 3d. So why is that? Well, it says electrons enter orbitals of lowest energy first. So why do we fill the 4s orbital before we fill the 3d? Because the 4s orbital is the first sublevel in energy level 4. Well, it has to do with total amount of energy. How many electrons does it take to fill the 4s orbital, or any s orbital for that matter? And the answer is 2 electrons. How many electrons does it take to fill the 3d orbital, or again, any d orbital for that matter? And the answer is 10, all right? So the amount of energy, the total amount of energy to put 2 electrons in the 4s orbital as compared to the total amount of energy to fill the 3d orbital with 10 electrons is less. Okay, and so 4s goes before 3d, and that pattern then follows its way, or follows the rest of the way through. So after the 4s, we come back to the next arrow. We go 3d, 4p, and then 5s, and then we go to the next arrow, 4d, 5p, 6s, and then the next arrow, 4f, 5d, 6p, 7s, and then 5f, 6d, 7p. Now, there are more orbitals in here based on the quantum number rules. We're going to talk about that here shortly. So each atomic orbital, 1s, 2p, 3d, contains, remember, both the number and the letter. The number corresponds to the energy level, or the principal quantum number, and the letter, s, p, d, f, etc., corresponds to a secondary quantum number, or a sublevel, which, remember, is the shape of the orbital path. Remember that each sublevel can hold up to this number of electrons, the maximum. Remember, S is 2, okay? P is 6, D is 10, and any F is 14. We went over all that yesterday. The second rule in regards to orbital filling is called the Pauli exclusion principle, named for Wolfgang Pauli. No 2 electrons in a particular atom can have the same exact set of 4 quantum numbers. And to occupy the same orbital, 2 electrons must have opposite spin. We went over that yesterday in diagramming quantum numbers, and we showed that for each electron, its 4 set of quantum numbers is unique. All right. Some electrons share 1 quantum number, or 2, or even possibly 3, but no 2 electrons share all 4 quantum numbers. They each have their own identity, basically. All right. And the last rule in regards to orbital filling is called Hund's rule. When electrons occupy orbitals of equal energy, then 1 electron enters each orbital until all the orbitals contain 1 electron with the same spin. Then additional electrons will complete filling the orbitals with opposite spin. So let me briefly mention that. We'll look at that again here in a little bit. Atomic orbitals of equal energy. Okay, so remember, for instance, a 2p orbital, all right, 2p. In reality, so 2p, all right, second energy level, p sublevel. P sublevel is where L equals 1, all right? So when L equals 1, M can have 3 values, -1, 0, and 1. Remember 3 orientations? Remember we had a 2px orbital, a 2py orbital, and a 2pz orbital because of the 3 different orientations. Each of those hold 2 electrons for a grand total of 6 in that 2p orbital in total. All right, but there are 3 individual p orbitals, px, py, pz. They all have equal energy. They're all 2p's. All right, that's what we're talking about here. We'll get to that here in just a little bit. So the 3 2p orbitals individually, and they all individually hold 2 electrons. All orbitals hold 2 electrons. But then the fact that there are 3 of them leads us to a total of 6 electrons, which is what it takes to fill an entire p sublevel. Okay. So let's go to our charts, and we'll get going on that. We'll come back to Hund's rule when it comes up again. So here's a much larger version of the diagonal rule, or the Aufbau principle. All right. Aufbau is a German word that means building up. A lot of people think it's a name. All right. It's not a person's name, but it comes from the German word for building up, which is basically what we're doing, building up the electrons in the orbitals. Remember, electrons fill orbitals of lowest energy first. That's what this rule says. All right. So remember our values of n, which go from 1 to 7, right? And our values of L, then of course, which go from 0 to n minus 1. Let's remember that as we look at this diagram, okay? So basically, I want you to see how this is laid out. If we look at it horizontally, all right? We look at it horizontally. So here's 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, and so on. If we look at this horizontally, we are looking at the energy levels. All right, we're looking at the energy levels. This is n equals 1, n equals 2, n equals 3, n equals 4, 5, 6, 7. Remember, Bohr thought that the electrons filled by lowest energy level first. And to a point, he was right. But there again, later, this theory disproved that. And so we filled diagonally rather than horizontally. If we filled via the Bohr model, it would be called the horizontal rule. All right. We would fill this horizontally, but we're not. All right. So let's look at the horizontal rows go by energy level. The vertical columns go by sublevel. All right, go by sublevel, SPDF. So these are S sublevels. 1s, 2s, 3s are orbitals. The S is the sublevel. So this is where L equals 0. Remember, L equals 0 is an S. This here is where L equals 1. Remember, there is no 1p orbital because in the first energy level, L cannot have a value of 1. All right. In the third energy level is where we first see L equals 2. All right, L equals 2, a D orbital or a D sublevel. And in the fourth energy level is first where L equals 3. All right, F, that's an F. All right. So let's talk about some other orbitals that we haven't mentioned yet, some other sublevels. All right. So let's look at n equals 5. All right. When n equals 5, L can be 0, 1, 2, 3, or 4. All right. So L can be 4 starting in energy level 5. Remember, we can go up to n minus 1. We don't have it here. All right? We don't have it listed there. It's there. All right. It actually has a name. It's called the 5G orbital. 5G. All right. Why isn't it listed there? Because we don't have elements with large enough atomic numbers to put any in there. When we do, we'll use it. All right. When we do, we'll use it. So in n equals 6, the sixth energy level, we're showing a 6s, a 6p, and a 6d. There's also a 6f. I mean, L can be 3 when n equals 6. L can be 4 when n equals 6. There's also a 6G. And there's also, in energy level 6, we can pick up another sublevel, another orbital, because when n equals 6, L can also be 5. We have a name for that one too. It's the 6H. The H orbital, the H sublevel doesn't appear until level 6, all right? Again, it's not listed on the diagonal rule because we don't need it, all right? In level 7, we do have a 7D. We do have a 7F. We do have a 7G. We do have a 7H. And also in level 7, L can be 6. So there is yet another sublevel and orbital in energy level 7. To my knowledge, it has not been named yet. So it's 7 question mark. I don't know what the letter is. I haven't seen it in any of the literature. But it's there. It's just empty. All right, it's not being used. And then the next question is, can there be an n equals 8? And the answer is, of course, there can be an n equals 8. That's the beauty of this thing. It just keeps going. The space is there in the electron cloud. All right, it's just not used. It's just not used. Our periodic table, as it's set up now, ends at n equals 7. But if we start discovering more elements, the periodic table's full. It's going to extend, all right, and it can. That's the beauty of the layout of the model. It can be extended to however far we need it to extend. So is there an n equal 8? Yeah, there is. There's an 8th energy level. It's just unoccupied. So there is an 8s, an 8p, an 8d, an 8f, and so on and so on and so on. And yet we pick up another sublevel too, because L can be 7. So this thing is extended. All right, this thing is extended. All right. Okay, go on to the next page. So let's review the filling of the orbitals. So it's, again, they fill diagonally. So you start with 1s. When you get to the end of one arrow, you go to the next arrow. 1s, 2s, 2p, 3s, 3p, 4s. Remember, here's where we veered off from the Bohr model, because the 4s orbital has less energy than a 3d. All right, and then 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p, and if we kept going, it'd be 8s next, and then 5g, 6f, 7d, 8p, and so on. It just keeps right on going. All right, keeps right on going. Now, let's go to the next page. Excuse me. Sorry. All right. Orbital diagram. Orbital diagram and electron configuration. Okay. I think we'll get to the filling of this chart today, and then we will call it a day. All right. Then we'll get to electron configuration in more detail tomorrow. So, orbital notation and electron configuration of the elements are 2 other ways of diagramming the electrons of the elements besides quantum numbers. We already know how to do quantum numbers, all right? So we're going to start, basically how this is, orbital notation is a shortcut of quantum numbers, all right? The little box here basically represents the first 3 quantum numbers, all right? The energy level, the sublevel, shape, and the magnetic quantum number, or the orientation. And the only thing remaining after the first 3 quantum numbers is the last one, which is the spin. So that's all we're going to fill in on an orbital diagram is the spin. The boxes are set up that already contain the first 3 quantum numbers. So we're going to do the elements in order, all right? So hydrogen, we're looking at atomic number now because that tells us how many electrons the element has. Hydrogen only has 1 electron. Well, where's it going? Well, according to the diagonal rule, we fill the 1s orbital first. And so we're going to put an electron in the 1s orbital. We always start with a positive spin, all right, like we did with the quantum numbers. So I'm going to put a positive spin electron in the 1s orbital, and that is it. That's the orbital diagram for hydrogen. Now, the electron configuration basically restates the orbital notation or the orbital diagram in a little different way. What are we showing here? We have one electron in the 1s orbital. The electron configuration is written 1s1. So the 1s, of course, is the orbital, and then the superscript 1 looks like an exponent. It's not, but it's placed that way. The 1 says there's one electron in that 1s orbital. Okay? So helium has 2 electrons. Of course, the first one is the same as hydrogen. Now, what about the second one? Well, the 1s orbital will hold 2 electrons. In fact, all of these individual orbitals hold 2 electrons. But yet it has to be opposite spin, remember? And so we put the second one in there with the opposite spin, pointing downward. And so the electron configuration now for helium is 1s2. We have 2 electrons in the 1s orbital. Now we go to lithium. All right, well, its first 2 electrons fill the 1s orbital. We have now filled that. The diagonal rule says, where do we go next? It says we go to 2s. All right, and so we will put a clockwise spinning or up arrow electron in the 2s orbital. Electron configuration, 1s2, 2s1. 2 electrons in the 1s, 1 electron in the 2s. All right. Beryllium, number 4. We're going to add the 4th electron, opposite spin to the 2s orbital. All right. 1s2, 2s2. Okay. Notice when you add these little superscripts up, 2 plus 2, you get the atomic number of beryllium, which is 4. You should, all right, because the number of electrons in that electron configuration or the number of arrows in this orbital diagram should be equivalent to the element's atomic number, okay? Boron, number 5. 1s2, 2 more in the 2s2, just like before. Now where's the 5th one go? Okay, well, we're going to the 2p, according to the diagonal rule, we're going to the 2p orbital. Remember, the 2p orbital is actually composed of 3 individual p orbitals, px, py, pz, for the 3 values of the magnetic quantum number, all right, -1, 0, 1. And so we will put 1 electron, clockwise spin, in the first 2p orbital, which is the 2px. So we'll have an up arrow there. Now, when we do electron configuration, we don't distinguish between individual p orbitals. We just lump them together as 2p. All right, so we have 1s2, 2s2, 2p1. All right, no x necessary there. When we get to carbon, I'm going to put a star by carbon. All right, and I'm going to say that Hund's rule starts here. All right, so let's put in the first 5, same as boron. Now the question is, where does the 6th electron go? Let's go back to the notes very quickly. And I want to read something to you again. Hund's rule. When electrons occupy atomic orbitals of equal energy, then 1 electron enters each orbital until all the orbitals contain 1 electron with the same spin. Then additional electrons will complete filling the orbitals with opposite spin. All right, so let's go back. There are 3 individual 2p orbitals, all with the same energy. All right, we've got 1 electron with the clockwise spin in the 2px. What Hund's rule says is the next electron goes into the next 2p orbital, the 2py, with the same spin. How do we know that? It's because of the magnetic properties of the elements. All right, magnetism, varying degrees of magnetism, is a result of an imbalance or balance of oppositely spinning electrons. If you have electrons, more electrons that are spinning one way than another, then we get magnetic properties. All right, this is what leads to magnetism. And so the greater the disparity between clockwise and counterclockwise spin, the more magnetic an element is. So some elements are not very magnetic at all. Some aren't at all. Some are slightly magnetic. some are more magnetic, and some are very magnetic. This is how we know that Hund's rule works, that Hund's rule is a part of the electron filling process due to the magnetic properties of the element. So, same spin in the 2py. But again, in electron configuration, we don't distinguish between individual p orbitals. So this would be 1s2, 2s2, 2p2. Okay? When we get to nitrogen, number 7, we put our first 6 electrons in, and where does the 7th one go? Well, we have another p orbital, the 2pz, and we're going to put 1 electron there with the same spin as the other 2, clockwise. All right, 1s2, 2s2, 2p3. When you get to oxygen, number 8, what did Hund's rule say now? Now we have 1 same spin electron in each of those 3 individual 2p orbitals. Now we go back and fill with the opposite spin. So back to the 2px we go with the down arrow for a counterclockwise spin. 1s2, 2s2, 2p4. Fluorine number 9 adds the opposite spin to the second 2p orbital. 1s2, 2s2, 2p5. Neon number 10 puts the last oppositely spinning electron in the 2pz orbital. 1s2, 2s2, 2p6. The p sublevel, all 3 2p orbitals, the 2p orbital as a whole, are full. All right? So, according to the diagonal rule, where do we go next? Well, after we fill 2p, we go to 3s. All right? And so, sodium, atomic number 11, we fill the ones prior, and now we go to the 3s orbital, excuse me, and put a up arrow for a clockwise spin there. 1s2, 2s2, 2p6, 3s1. All right? And then magnesium, number 12, fills the 3s orbital with the opposite spin. 1s2, 2s2, 2p6, 3s2. And if we were to keep going, all right, next after magnesium is aluminum. If we were to keep going with aluminum, number 13, well, according to the diagonal rule, what orbital fills after 3s? And the answer is 3p, all right? And so aluminum would have all 12 of these full. And then we would have a box for the 3px. Remember, there's 3 individual p orbitals, so there's a 3px, a 3py, and a 3pz, just like there is in level 2. And we would put 1 electron up clockwise into the 3px orbital. 1s2, 2s2, 2p6, 3s2, 3p1. Okay? And then on we go with silicon. All right? Same thing, same pattern. All right? Same pattern. So let me take a look at the assignment here. I think we are ready to finish it. Double check that. Pull it up over here. I know it's here somewhere. There it is. And I would say, according to this, yes, we can finish the assignment. I want to go back very quickly to our notes and look at something that we did yesterday. All right, so let's pull the notes back up. And we're going to back up. Let's see. All right, so here we are. We're going to back up a couple of pages to where we diagrammed the quantum numbers for carbon. We did this yesterday. I want to bring something to your attention that we did not know yesterday, but we know now. All right, so As a quick review, we'll fill these back in. So remember, for carbon, it had 6 electrons. So we had 1, 0, 0 clockwise and 1, 0, 0 counterclockwise. And then we had 2, 0, 0 clockwise, 2, 0, 0 counterclockwise. All right. As we know now, of course, these are the 1s2 electrons. These are the 2s2 electrons. And then we said 2, 1, negative 1 up, and 2, 1, negative 1 down. These then are the 2p2 electrons that we just talked about a few minutes ago. But now I want to bring something to your attention, all right? And that is Hund's rule, all right? So let's look back at that. Remember, we said that carbon is where Hund's rule starts, all right? Because once you put that 5th electron into the 2px orbital, in reality, that 6th electron goes in the 2py orbital with the same spin as the 2px, which was clockwise. We did not do that here with its 6th electron, all right? So technically, these first 5 are correct, but the order, the exact order that the electrons fill via Hund's rule, this 6th one is not correct. What would it be? Well, it would still be 2, 1, but instead of negative 1 down, negative 1 represents the 2px orbital, 0 represents the 2py. So we would go 2, 1, 0, and then up. Same spin clockwise as the 2px. So in reality, again, this is okay in regards to the number of electrons that are in carbon in regards to quantum numbers, but in the exact order that they are filled, this 6th one is actually 2, 1, 0 up, all right? Same spin as 2, 1, negative 1 up. And then, of course, nitrogen, which would be next, the 7th electron would be 2, 1, 1 up. Then when we get to oxygen, remember we went back and started filling electrons with the opposite spin. We would have then went 2, 1, negative 1 down, and so on. All right, just wanted to bring that to your attention to make sure that from here on out, now that we know it, that we would do the quantum numbers in the exact order that they fill. All right, which we just learned from the orbital diagrams. So I think that ends today. So that's a lot. So now we know how to do orbital notation, and we got an idea of what we're going to do with electron configuration. We'll get more into that tomorrow. And so I just want you to finish the assignment that you started yesterday. Keep in mind, we do have a test coming fairly soon, kind of looking like Tuesday. Hopefully I'll have an answer on that tomorrow. So until then, everyone stay safe. Keep working hard. Stay focused. All right, stay focused. We're getting through this modern atomic model pretty well. Let's get her done to the end, though, shall we? Until next time, I'll see you. Take care, everybody. So long.